Good morning, everyone. I hope you are doing all right this morning and hoping you are ready to learn some physics. So after finishing kinematics, we started talking about dynamics last class, and we learned about 3 laws of motion that talks about the effect of force on the motion. So while talking about 3 laws of motion, especially first and second law, we talked in terms of net force, means sum of all the forces acting on the object. That's what determines the motion. If net force is 0, object is moving with constant velocity, but when net force is not 0, then velocity changes, means accelerates, and uh, the acceleration can be found by using Newton's second law. So in both cases, we have to find out the net force, not just a force, but net force acting on an object. So how do we go about it? So that's why we need this free body diagram that shows you all the forces acting on the object. Not just object, but object of interest. What is object of interest? The object, uh, to which we are trying to find the motion of. Okay, so for example, in this case, you see near the bottom of the slide, this person is pushing this car using this applied force. So if we want motion of this person, then the person is our object of interest. If we want motion of the car, then car is our object of interest. Similarly, you see here, mom and kid having fun here, and they are at the beginning of their act. So if one person gives a push, both of them gonna start sliding or skating on the ice. So depending on whose motion we want, for example, if we are interested in motion of mom, then mom gonna be object of interest. If we are interested in a kid, then kid gonna be the object of interest. So first you need to figure out motion of which object. If we want motion of both objects, then we need to draw 2 free body diagrams following the same rule for each of them. Okay. And I think we talked about this one last time as well. So identify the object of interest, and that's what I just talked about, and identify the forces on the object of interest. So when we talked about these different kind of forces last time, which I have listed them here on the side as well, one force of gravity, is always there as long as we are near the Earth's surface. So it's always there. So you always have to draw this force, what we call force of gravity or weight, or simply we denote that by mass times acceleration due to gravity, because force is mass times acceleration. So the acceleration caused by the force of gravity is lowercase g, we learned. So that means we can also write that force of gravity as m times z. So that's the only long range force, and it's always there when you are drawing free body diagram, unless we are talking about object in space where gravitational force is negligible. Most likely we're going to be talking about objects near the Earth, so it's always going to be there. So your free body diagram should always have that thingy there. And then now the remaining forces, these we call contact force, and they can be applied only by touching them. If you're not touching them, if something is not touching them, that means that thing or you are not applying that force. So keep that in mind. Sometimes we think, okay, the force we pushed something with is still there, although we're no longer touching it. Okay. Once we're not touching it, once it gone from our contact, we're not applying that force anymore. So that force does not go in the free body diagram. So keep that in mind. So all these comes from the contact of some sort of thingy. Okay. So look one by one, cycle through your head. Is normal force acting? Is friction force acting? Is tension force acting? Is there some sort of applied force? Okay, cycle through all these contact force, and whichever you think are acting there, draw them. And that's what this part is talking about. Okay, identify the forces on the object of interest and replace the object of interest. So now once you have identified, okay, these are the forces acting, you can replace object of interest by a dot and then draw those forces. And these forces has to be drawn starting from the dot, not ending at the dot. So this arrow shouldn't be ending here. Rather, you can move this arrow over here and draw there. It's the same thing. Okay. So we don't draw like this. Rather, we draw all these arrows, as you can see, starting from the dot. Okay. And then what happens? What's the purpose of drawing free body diagram? Eventually, we want to use it to write Newton's law. And Newton's law is about sum of forces. And we always write that along the x direction, something like this, and y direction, something like this, separately. So since we use that separately in two perpendicular directions, we also choose a suitable coordinate. Okay. So for that, we try to choose a coordinate that contains the maximum number of forces going through the chosen coordinate. So for this free body diagram, if I were to choose coordinates, one would be horizontal, another would be vertical. That way, all these forces are lining up along that direction. But sometimes we may leave a force that may not be pointing in the our choice of x and y axis. In that case, you have to find or write down the component of that force. Which force? The force that's not pointing along either x or y direction. So that's why learning, not just learning, but being fluent on writing component is very important. Okay, component of a force. How do you do that? So for example, in this case, you see this tension force maybe at incline to the horizontal. So when we choose horizontal as a x and vertical as a y, it's a good choice because it contains two of them, actually three of them, right? But tension is neither pointing along the x direction or y direction. So in that case, we need to find component of this tension force, okay? So for that, we need either this angle or that angle. I think if I remember correctly, we may have polled on this, but just in case, let's do a polling here for this question. And you have total a minute and 30 seconds for this. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So mostly B, and that is correct answer. So A is close, but see, we did not replace our system by object, the dot, our object of interest by dot. So here we have done that. And why these are not correct? Because dog is not pulling the sled. Ooh, how could you say that, Ramesh? It's the dog that's pulling the sled. That's we have heard. That's what we say. But that's what we have to be careful about. Dog is not touching the sled. It's the rope that's touching the sled. So that means without touching, dog cannot apply force on the sled. Instead, what's happening? Dog is pulling the rope and rope is pulling the sled. So that's the difference there. So that's why these cannot be correct answer. So in free body diagram, another thing you want to keep in mind is only forces belong in free body diagram. Sometimes we may draw velocity, acceleration, but we draw them on the side, not from the dot, because they don't go in the equation sum of the forces. Okay, they don't go in the equation, the Newton's laws equation, which says sum of the forces in a particular direction is equal to mass times acceleration in that direction. So we may, to keep track of motion, we may draw acceleration and velocity on the side somewhere, but not from the dot, not from the object of interest, because they are not forces. Okay. Okay, with that said, now we have another question related to free body diagram. In this case, it's not labeling the forces, okay? But forces are there. So it says velocity constant, and this arrow means it's simply moving in that direction with constant velocity, okay? This arrow over here, arrow over here simply means it's moving in that direction, and it says v constant means velocity is constant. Okay, so now your job is to figure out what forces are acting on the object. Here it says, assume there is no air resistance or friction. Okay, so here air track has this special setup where, tiny bit of air comes out straight up and lifts the object slightly from that so that friction becomes negligible. Okay. So with that said, I'm opening the poll, and now you have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. So A and D competing, and others are there too. Okay. So let's say, like most of you, if I'm thinking A is correct answer, am I right or wrong, and why? Feel free to turn on your microphone and speak, or you can also type on the chat. I'll give you a minute. Is A right or wrong? If I'm saying A is right, am I right or wrong, and why? So am I right or wrong? You did not answer that. You have to start by saying right or wrong. Okay, I see one response there. So A is right. And because there is no contact force, just mg and the normal force. Okay. Okay, why is there no contact? You mean applied force, I guess, right? Remember, normal force is also contact force. And so, yeah, you mean no applied force. How do we know there is no applied force, although it's moving? So yes, applied force, nothing pushing or pulling it. There is no string attached, right? And so that's one way to look at it. And there is another response that says there is no friction or air resistance, nothing will slow down. So it's not slowing down, right? It's moving with constant velocity. So it's moving with constant velocity. That means net force is zero, or sum of forces in this direction, let's say this is the x direction, is zero. So if there is no friction or resistance, so that means there is no backward force. So when there is no backward force, you don't need forward force to keep it moving. Okay. So otherwise, if this one, and that one was correct, then this would be accelerating because there is net force in horizontal direction, and that net force would cause the acceleration. Okay. So yes, it seems like, D is also correct answer, but it is not. And that's to understand that, we have to totally understand what Newton's first law is, right? Object can keep moving with constant velocity, even if there is no net force acting in the direction of motion. So in this case, since there is no backward force, we don't need forward force as well to keep moving it with constant velocity. If there was just forward force, then that would accelerate it. So this free body diagram would mean that this is accelerating. But the question clearly says it is moving with constant velocity. So yes, A is correct answer in this case. So here See, there is weight is missing here, which cannot miss. We cannot miss because as long as object is around, is there. So yes, air tries to lift it, but it's still kind of on that surface. So we can say, okay, there is normal force. Okay. And there is a normal force. So yes, A is correct answer here. So now here is another. So there are 4 choices and there are 2 questions, possible questions we can make for 2 different situations. So first, let's ignore this. Okay, second or B. First, just look at A. It says it is about elevator. So object of interest. Object of interest is elevator. So what is the tension on the string when it is accelerating up, right? So that's the question. And when do we know it's accelerating? So one way to look at it is, okay, when it's moving up, it's accelerating up. That may not always be the case. Remember, when it's moving up, it's accelerating up only if it's speeding up. So even if it is moving up but slowing down, acceleration is not up, it's down, opposite to the motion. So keep that in mind, okay? So when we could say it's accelerating up. So to describe that, I have this thing on the parenthesis, okay? It's accelerating up when it is moving up and speeding up, or when it's moving down but slowing, okay? Moving down but slowing. Even when it's moving down, it could be accelerating up. When is that? When it is slowing down. So for example, you come from the upper floor and your elevator is about to stop. What happens? It slows down. It's moving down, slowing down, means acceleration is up, okay? So now, let's say this is the case. So now, question is, which FBD is the best with acceleration drawn on the side? So there are 4 choices, okay? So you have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. So we got all of them, but D got a bit more. So here object of interest is elevator, and elevator is moving. So that means it's not supported by any floor. Elevator is basically just, you know, the box hanging on the air, supported by rope, right? So that means it's not supported by any surface when it's moving, okay? So that means there is no normal force acting on the elevator, okay? So that means we cannot have this and that. No normal force here. See, the elevator is not supported by anything here, okay? So that's why A and B cannot be correct answer. Now, about C and D, as it says acceleration is pointing up, okay? So that means that, yeah, otherwise there is no difference between these two. So to differentiate that, we have to look at the acceleration drawn on the side of the free body diagram in this case, okay? So it says accelerating up means we need to write something like that. Okay, so D is correct answer for this case. So now let's write equation, Newton's law, to find tension. So how do I know I have to use Newton's second law? So tension is a force. So we are trying to find force. And the acceleration, it talks about acceleration. So acceleration is a given. So forces and acceleration, they are related by Newton's law. So that's how I know I have to use Newton's law here. Kinematic equation, they don't have force. Means we cannot use them to find force. Okay. And so far we have only learned about kinematic equations and Newton's laws of motion. Okay. So only two main tools we have, only two basic physics we have learned so far. And based on that, when I have to decide, do I use kinematics or dynamics? How do I decide? So this is how I decided, okay? So here, the forces are acting along the vertical direction. So I wanna use the Newton's second law in vertical direction. And here I'm saying vertical direction as a y. So for that, I need to be more specific. Let's say vertical direction is y and is up positive or down positive. I also need to be clear about that. So let's choose up as a positive. We can also choose down as a positive. Answer will be same, okay? But the intermediate equation may look slightly different, okay? If we choose down as a positive. So now, so let's pay 100% attention. This is one of the most important skills, okay, in physics. How to, once you have drawn free body diagram, how to use that free body diagram in Newton's law to write equations so that you can solve problem, okay? So for that, you need to read this equation like this. So pay attention. Sum of the forces along the y direction. Again, sum of the forces along the y direction is equal to mass times acceleration in that direction. So forces are vector. So when we write them in equation, we have to have positive and negative sign properly written. Acceleration is also a vector. So we have to make sure that we are writing the positive or negative sign instead of the direction. Okay. So now, once I decide, okay, I'm using this to this, then I look at here while reading this sum of the forces along the y direction. So that means in y direction, that means vertical direction here. I need to add all forces acting in vertical direction. So how many forces are acting in vertical direction? Can you type that on the chat? How many forces? 1, 2, 3. How many forces are acting along the vertical direction in this free body diagram? Count the number of forces, count the arrows basically. That starts from the dot. Okay. So I see 3. So are these all 3 forces? So for example, this one says acceleration. So acceleration is not a force. So we have to be careful on that. So I have one force, tension, pointing up and weight pointing down. Only 2 forces. Acceleration is not force. So when you count the arrows, you need to count the arrows that is drawn from the dot, which are the forces if you drew them correctly. Okay. So 2 forces. So we need to add them. So what's the sign of tension here? Is it positive or negative? Based on our choice, is the sign of tension positive or negative? Can you type that on the chat, please? So I see some positive there. So yes, positive. It's pointing up, and we chose up as a positive in this coordinate. So I write positive t. So although we may not write positive sign explicitly in the first term, we may not write sign, but I like to write that while going from this equation to this equation. Okay, while writing or expanding this equation, I like to write that explicitly. Why? It's because I want to make sure that I took account of the direction of the force while writing the equation. Otherwise, it may just slip off if we don't pay special attention to that. Okay. So another force is pointing down. So when up is positive, down automatically means negative, and we are writing that as a W. Okay. So that's the sum of the forces, folks. That's the sum of the forces in this, based on this free body diagram. See how important drawing free body diagram is. I hope you realize that. So while writing this equation, you totally rely on that free body diagram. Okay. So now we need to move to the right-hand side of the equation. Left-hand side is done. Great. So now let's move here. So it has a mass. Mass does not have sign because mass is a scalar quantity. It does not have direction, means we don't need positive or negative sign for the mass. However, acceleration is a vector. So that means we need its direction. And since we are writing acceleration in equation, we need to write correct sign, positive or negative, based on our choice of coordinate. So in this case, our choice of coordinate up is positive. And when I look at the acceleration here, it is also pointing up. So that means acceleration is positive. So you do not want to write M and positive A, that has different meaning, right? So that means you are adding mass and acceleration. So if you want to do that, you have to put parentheses here. But usually what I do is, since mass doesn't have sign, I put the sign in front of the whole term because positive A times mass is positive mass times A, okay? So if I have positive 2 times 3, what is the result? Positive 6, okay? So I can just write that positive in front. So that's what I would do. So before I write this, I would look if I know the direction of acceleration, and that's going to determine the sign of that thingy there. Okay. So one exception, if you are just trying to find the acceleration, if you are just calculating acceleration, then you can leave this ay as it is and solve this equation for that ay that gives you the acceleration. Here we are assuming that we know the acceleration of the elevator. Value we know, we also know the direction. Okay, so that's what we are assuming, and based on that, we are replacing acceleration in vertical direction by its value, which is A, and its direction, which is positive. So that's what we are doing. So yes, what happens is you need to do practice of drawing free body diagram and then writing the equation. And always, always, always start by writing the main equation, main law, main formula. Okay. Do not just start writing something like this. Okay. So there is a question, what if A is negative? So M times negative A, what is that? 2 times negative 3. What's the result? Negative 6. So that means this will have a negative sign in it, right? Good question. Okay, that said, now let's move to B. So this is done. Okay, it's done. Now let's look at here. So we're not talking about this, rather we are talking about this, okay? B. So which free body diagram, so I'm writing in short FBD, is best. Remember, to use Newton's laws, you always have to draw a free body diagram. If you're not drawing, it's like throwing a stone in the dark. Okay, you may hit the target, most likely you may not. Okay, so I'm opening the poll, and this time it's just 30 seconds for you. Okay. 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. So mostly C. So basically, yes, that is correct answer. So we cannot have normal still. It's the same problem. Only thing that changed was going from A to B is the direction of acceleration. So basically, C is correct answer in this case, right? So now, how do we write Newton's law? So forces are still in vertical direction, right? Acceleration is in vertical direction. So you start by writing same equation, Newton's second law in vertical direction or y direction. Here, let's use the same coordinate, means up as a positive. Now, just like we went from here to here, can you go expand this to this free body diagram? Go ahead, write the equation. I'm hoping you have some sort of paper, pencil on your side or something, somewhere you can write on. So go ahead, complete this equation. And once you have completed, type that on the chat, but make sure it's written on your device or paper before you type on the chat. So I want equation like this for this free body diagram. I'm hoping everyone is writing equation. It's just one equation to go from there to there. So you can all watch all day everyone else writing equation unless you write and practice it. Use your head. You may be always stuck. So that's the opportunity I'm giving you here. Write it down. Don't worry if you're going to be wrong or not. Okay, write it down. That way you'll focus on the problem and later you can correct it easily. So I don't see anybody typing on the chat their equation. It shouldn't be that difficult to type here. Okay. So I see two of them. They look kind of, basically they are same. Okay. So just two people can write the equation. Okay. 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 It increased the number. Okay, I see all equations are same except the very last one that came. Okay, that is not wrong, but while going from here to here, probably is not, it shouldn't look something like that. See, we chose up as a positive. So that means T should be positive here when you write it. Okay, and then W negative. And acceleration is down, so that's why it's a negative. So mass times negative acceleration is negative ma. So based on this free body diagram and this coordinate, yeah, you should be writing something like this first, okay? But of course, this equation is same as this equation as well. If we change the sign of everything, this can be written something like this. Or if we choose down as a positive, if we choose down as a positive, then what happens? This equation shows up naturally, okay? W positive, so that, and T now is negative because we are choosing down as a positive, okay? And then acceleration is positive because we are choosing down as a positive. So if our choice of coordinate was this would be the second equation after that. But since we chose this, probably, we should be writing first something like this. Okay. So again, this is not wrong, but it is not the direct translation of this equation to this free body diagram and this choice of coordinates. Okay. So yes, thank you for writing that way. I was able to show it, like how that can be obtained, right? And correct. So yes, of course, who said I have to choose up as a positive? I can choose down as a positive. right? So when you choose down as a positive, then it becomes just this, yes. And I would write positive in front of weight, okay? So, so for this coordinate, this, and for this coordinate, this. But essentially both are same once we rearrange the terms. So physics is still same. Physics cannot be different based on choice of coordinate. But the way the equation looks in the intermediate term could be different, okay? It may look different, okay? Okay, so that is that, folks. So now our weight, we said, is mg. It comes from the gravitational pull on us, okay? As long as we are near the Earth's surface, what happens? It is mass times acceleration due to gravity, because weight is a force, and force, it is a force due to gravity. So that force is mass, our mass times acceleration, but this acceleration being a special acceleration, acceleration due to gravity, we write that A as a Z, okay? And it is always vertically down, okay? So that's the weight. But when we are accelerating, what happens? The reading of the scale not going to be mg. So let's suppose you put a scale on elevator that shows your weight, okay? And you stand on it. So when elevator is not accelerating, what happens? Your weight gonna be m times g. And of course, your scale may change that mg reading to just mass by dividing it by g, okay? And it may simply show you the kilogram, okay? It can be written in terms of kilogram, but it is actually, it should be, weight should be, you know, the force, okay? And its unit is in Newton. So now, when you are accelerating, the reading of the scale is not equal to mg. And how do you find out your weight? By looking at the reading of the scale, right? So when you look at the scale, your reading is different. So your weight is no longer mg at that time. So what we say is, okay, that weight is your apparent weight. So when you are accelerating, your weight changes, and we call that apparent weight. Weight is always, we write mg, okay? So now, what's the new weight? When object is accelerating, we call that apparent weight, and that comes from the normal force in the equation. How is that? So when you stand on a scale, what happens? So your weight is pulling it down, and then what happens? Since you are supported by a scale, there is normal force, and the scale measures the normal force, okay? And that is your apparent weight. So now, whenever you are asked to find apparent weight, what should you look for? Not mg. Look for normal force on the accelerating object. That's what you should look for. Is that clear, folks? Did you pay attention? Apparent weight means normal force. That's what you are calculating whenever you are asked to. Okay, so that's what I have written here as well. So here is a video from the reference book. Okay, so we have a textbook, and mostly I provide notes. So for most of the time, you may not even have to look at the book, but we have a OpenStax textbook, right? Ebook, which is free. And I have also listed a reference book in a syllabus. So if you want to hold a book, keep the physics book around, that reference book is good one. Does not matter which edition it is, okay? It is a good book. So that means, so it looks like there is a question on the chat. So why not always just compute n for W and you won't have to worry if it's accelerating or not? Yeah. So you can compute n. So when it's not accelerating, n becomes mg. Basically, if we are talking about vertical acceleration, but if you are accelerating in different directions, so in that case, we may have to think about it, okay? So that's a good idea. So here is that video. So in this video, what happens is professor is inside an elevator, but you don't have to pay attention to the professor. There is a scale that has a needle, and there is a candy. Oh, candy. We're in the elevator, and we're moving. Ooh. We're in the elevator. So this is what I'm talking about. So right now, look at the reading of the candy. It's showing 20 and one line more. So there are 5 lines between 20 and 30. So that means each division is 2. And I think it's in Newton. So it's showing 22 newtons. Okay. So right now, elevator is not accelerating. You want to see what happens when elevator accelerates. So pay attention to this needle. And I have a question for you. Does this needle deflect towards larger number or smaller number when you see the deflection? So when an elevator is accelerating, what happens? You will see needle deflects a little bit, okay? And then you want to pay attention, is it deflecting towards larger than that 22 or smaller than 22? So you want to type smaller or larger, whatever you see. We're in the elevator and we're moving. We're moving at a constant speed. Acceleration 0, net force is 0. But now, watch what happens. There's a small bump. And so what did you see? Was the scale going towards larger value or smaller value? Or how many of you did not see what happened? You can also type, I didn't see. I'll run the video again. Okay, so it deflects towards larger value. Okay, so that means apparent weight of this candy is larger. So that means, is it accelerating up or down? Is the elevator accelerating up or down? Can you answer that question? That's what this professor is asking question, okay? Okay, I see up, and how do you know it's up? Can you write equation that shows you this n is larger than mg? So how do you draw a free body diagram? Okay. So here is very similar exercise that we did. So before it was object of interest was elevator. So now it's not elevator, it's a person or object on the elevator. Object of interest. So now for this A, which F, B, D is the best. So that's the question. So there are 4 choices. So go ahead and you have just 30 seconds for this. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got here. Mostly B, and that is correct answer. So now C and D are incorrect because there is no tension force acting on the portion. Okay. Remember, tension force acts from the rope or the string. In this case, cable is not attached to the portion. Okay. So portion goes up and down because normal force is acting on the portion. So that's why free body diagram would have normal force and weight. But since it is accelerating up, it says, so this is the best. So now, how do we write the equation then? Sum of forces along the y direction is mass times acceleration in y direction. Where is y direction? Let's say up is a positive y. So now after I have this, now I can start writing or expanding this equation. Normal force is pointing up, so positive. Weight is pointing down, so negative, because we chose up as a positive. So that's the left-hand side. And right-hand side, mass and acceleration is also up, and we said up is positive. So that means it's going to be positive MA. So now we are looking for normal force. So that means it's going to be MA plus W. See how this normal force is larger than W by this mass times acceleration. It's like this equation. For example, I'm putting some random number here. Let's say when it wasn't moving, weight was, let's use the number we saw in the elevator. It was 22. Okay. So now normal force is 23. It's larger. So by how much? Then most likely 1. So you see that this weight is smaller than normal force, or normal force is larger than weight. Okay, so that is when object is accelerating up. Now, how about accelerating down? So for that, we have to use this free body diagram. And let me write the same equation here without copying it. So again, force is normal is up, weight is down, but acceleration is down means it's going to be negative MA. So when I solve this one for normal force, so here this W has a negative sign. When it goes to the other side, it becomes positive, and MA is negative. So now you see the normal force is less than weight. And by the way, weight can also be written as a mg. So let's write that. And also, let's factor m out. Okay. So now, when A is equal to Z, what is normal force according to this equation? Can you answer that? When A is exactly equal to Z, what is the normal force? Can we figure out normal force in that case? Means apparent weight of the portion. So what do we do? M G is there, and replace A by A equal to Z means replace A by G, means it is in free fall. Okay, it is in free fall. When acceleration is equal to 0, we say object is in free fall. Okay, so now G minus G is 0, so that means it becomes 0. So the apparent weight becomes equal to 0, means the person doesn't feel weight. So person feel what we call weightlessness, okay? Weightlessness. So that's what this person is feeling, okay? Wherever acceleration is equal to Z, the person gonna feel weightlessness. Person gonna feel like, okay, they are floating. So for example, if someone jumps off from the roof, which I'm not asking you to do, don't do it, okay? That's when you feel the weightlessness. But when you are in an elevator and when, the acceleration, so for example, let's say you are going up and then elevator is about to stop somewhere, then your acceleration is down, right? It's slowing down, means acceleration is down. So in that case, you have this weird feeling in your body. I don't know if you have paid attention. Next time, pay attention to your body, how it's reacting when it is about to stop. It feels like, hey, is it falling down now for a while or something like that, right? So it is because you are used to your weight as a mg. So when it's different, it feels different. And you'll also feel that little bit difference when it's going up, but it's not that much, but when it's coming down, a lot. So when you are in Ferris wheel, let's say, not the kind of Ferris wheel that you just use to see the, view of the city. The Ferris wheel that kind of actually spins a bit faster. Vertical Ferris wheel that kind of relatively spins faster. In that case, what happens? This bucket, when you are near the top, the bucket becomes horizontal. And then once you start coming down from the top, bucket suddenly drops. So over there, you have near free fall experience. So that's why you feel weird. And that's when you hear the scream, or even sometimes you may also see people vomiting there if it's going fast. Okay. And I think Ellis Garden has a tower where it brings people up and then let it fall really fast. Okay. So it's not totally free fall, but it's accelerating down. So that's when you hear the scream. So what's happening? They are feeling less weight than the normal. Okay. So that's what's happening. Okay. So that's the apparent weight, folks. Oh, it's already 9:04. So it's a good time to take break. Once we come back, we're going to pull on these two questions. So let's take 5 minutes break. Hey folks, so welcome back. So since these two questions are related, I am basically bringing them together. But first, let's pull on this one here. And you have 1 minute and 30 seconds to answer this question. 30 more seconds. Can you draw a free body diagram and write equation for this? Try that. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see how did we do here. So mostly A, which is correct answer. And I know from that elevator example, remember, the elevator was accelerating up there and reading was larger. But how do you do systematically? You draw a free body diagram. So normal force is the force from the rocket. Here, portion is object of interest. So rocket floor of the rocket is, applying normal force and holding the person on the floor. And weight of the person is there. And rocket is accelerating up. So let's say up is positive y, or maybe let's do down is positive this time, just to see, how things change. So positive mg minus n is equal to minus ma. So now I want to solve for n. N has a negative sign, so I'm going to bring it here, and I'll bring it there. So it becomes mg plus ma is n. So normal force is bigger than weight of the person. Okay. So yes, it would have been even simpler if we had assumed up as a positive. Okay. But anyway, so that's that. So now here is another related question. So upward force exerted by the rocket floor, okay, normal force, and the downward force of person on the rocket floor. Okay. Which one is bigger, or are they equal? So that's the question. And you have a minute to answer this question. Thirty more seconds. And this is 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so now if we pay attention, what do we see here? Oh, by the way, what did we get? Okay, so B equal to, and that is correct answer because I know there is talking about action and reaction forces. Okay, the upward force exerted by rocket floor on the person and downward force of person on the rocket. See how these are the interacting forces talking about, okay? Okay, so that's that. So now, moving on, here is another question. So I'm holding something like this, marker or pen or a ball. So what do you think? And you have total a minute to answer this question as well. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. See, there is no net force acting is mostly, selected, and that is correct. It's not accelerating means net force 0. Newton's first or second law. Okay. So if I were to make free body diagram, what happens? The weight is always there, right? Weight is always there. Object is not weightless. And I'm applying some force to hold it. So to counter the gravitational pull or counter the weight. How much force I'm applying when I'm holding this versus I'm holding this. If I know weight of these, I'm applying exactly same amount because I'm not letting it to accelerate. Okay. So net force is 0. So that means F positive, let's say assuming positive as a up as a positive. So how much force you are applying when you are holding something? Exactly equal to the weight of that object. Okay. So that's why holding a ball is not that bad. Holding up on the air. Try holding up a couch on the air. Okay. Why different? Because they have different weight. Okay. So now here is a video of an object. We call that fan cart because there is a fan, little fan attached to this cart. Okay. And in this case, what's going on? You give a push and let it go. Okay. What happens? This one slows down, and then after reaching somewhere around, it kind of turns around. Okay. Let's watch video. So short video, if you blink, you may miss. Okay. So what do you see? Did you notice once it leaves the hand, it starts slowing down. And then somewhere around here, it briefly stops and then turns around and starts moving this way. Okay. So now here is question for you with some choices. You have a minute to answer this question. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got. So A and B kind of competing. Okay. And we also see there are some choices for C. So correct answer is A. So why C is not correct answer? See, velocity of the card is changing. So whenever velocity changes, the object is accelerating. So keep that in mind. So it is accelerating away from the hand or to the left. So see, it started slowing down. So motion is in this direction. So speed is in that direction, velocity, and acceleration is in this direction. How do I know acceleration is in this direction? Because it's slowing down. If something is slowing down, acceleration is in opposite direction while going this way. And remember, from Newton's second law, what do we know? Sum of forces along a particular direction is mass times acceleration in that direction. So whatever direction the acceleration is, the net force is also in that direction. Okay. So along this direction, we look at the forces in this direction. We see the acceleration is to the right, means the force must also be to the right, because force and acceleration, net force and acceleration in that, direction is, they are same, always same. Now, how about when it's coming back? So when V is this way, it's speeding. Okay, its speed starts increasing. Speeding means acceleration is in same direction. So acceleration is always to the right. So that means force is always to the right. And that situation is no different than this when we throw a ball vertically up. Motion looks very similar. Only difference is there is horizontal direction. It's happening in horizontal direction. Over here, it's happening in vertical direction. Okay. So when we throw this, what happens? It slows down. We say, okay, acceleration due to gravity is down. So is the force of gravity. It's pulling down, reaches to highest point. And then what happens? It starts coming down, speeding up. So acceleration is down, force of gravity is down. So similar. So where is that force coming from here? Not from hand. Once we release, it's not contact with the hand, so that force is not coming from hand. It's coming from the fan. So when fan, remember the boat on the water, when it spins, it propels the water and then that propels the boat. Okay. Similar situation is happening here. So now I see there is a question. So is weightlessness possible on the x-axis, right and left? So when we define weight as, let's say, due to the gravitational pull, then probably x direction or horizontal direction not going to make sense. Okay. I'm answering question on the chat. Okay. It says, is weightlessness possible on the x-axis, right or left? But, we can create artificial weight and artificial weightlessness. Okay. And that is possible. So in that case, so in general, I would say in our general sense of weight, no. But probably in some sci-fi movies, you may have seen, like there is something, this, they are on the galaxy somewhere or something in this space, and they have this platform. In that platform, they are behaving normally as if they are, on the Earth. So what they are doing is they are creating artificial acceleration. So, for example, when something is spinning, what happens is there is acceleration. When something is moving in circle, there is acceleration always towards the center of circle. So that acceleration may act like a that gives you the weight, your weight. Okay. So in that case, you may feel like, okay, there is that weight. And then suddenly what happens? If that's gone when your acceleration, that acceleration becomes equal to z, you may feel like g in this case is whatever that acceleration is, you may feel that. So yes, I'm not ruling out it's impossible to have it, but in our general sense, weight is in vertical direction means weightlessness is also kind of, it's count, that's when we feel the weightlessness. Okay. Good point. So now moving on, here is a question about, sailboat. I was just talking about boat. So here this sailboat is propelled by the air. Okay. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. So we are getting B and C, and we also have A and E. Okay, so net force we're talking about. So constant velocity means net force is zero. That's Newton's first law. We don't even have to draw a free body diagram. Okay. Net constant velocity means net force is zero. So if I were to draw a free body diagram, how would it look like? Mg, and let's say normal force, and there is force from wind, applied force, and there is some sort of friction force from maybe water. Okay. So the wind force is just pushing this to balance the drag from the water. It's called drag, friction. Okay. So they are equal. So it may seem like, okay, wind is pushing that way, it's moving that way, there must be force in that direction. But yes, there is force, but this question is about net force. Okay. So net force is zero whenever velocity is constant. So if you miss this question, that means you still need to, understand the Newton's laws. Okay. So I keep bringing this kind of question to remind you object can keep moving with constant velocity even when net force is zero. So reminder, that's what Newton's first law says. So C is correct answer in this case. So now here is this question. So we talked about, vertical direction, and of course could be horizontal direction. How about at incline? Okay. You push something at incline. What is the direction of net force when block is at maximum height? So you give a push, just like that fan cart situation. Here there is no fan attached. There is force acting because it's an incline. So you give a push, so you give some starting velocity, and it goes up, and eventually maybe comes back. That's what it says. Reaches to a maximum height and finally slides down. So what is the direction of net force when block is at maximum height? So for example, if it goes all the way here and then it starts coming back at the moment, what is the net force? Okay. So I am opening the poll and you have a minute to answer this question. Thirty more seconds. Five more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. Oh, we have varieties of answer. Okay. 0 force at maximum height, so no direction is A. If the force was 0, why would it come back? Right? At the maximum height, it stops briefly. If no force is acting, why would it come down? It's like your parked car suddenly starts moving, right? So that's not possible. So there is force, and it is B, down along the plane, okay? So how do we look at that? Before we do that, let's look at another question. So now it is direction of acceleration, okay? What is the direction of acceleration? And this time you have only 30 seconds. Okay, 5 more seconds. 5, 4, 3, 2, 1, and it stops. So now let's see what we got here. So we got all three. So it is always, that's what the Newton second law says, okay? So in this case, net force is downhill, means acceleration is also downhill, no matter where it is, okay? So for that, let's look at free body diagram, okay, of that object. So how do we draw a free body diagram of an object at inclined plane? We replace plane by a dash line and put a dot, okay? And then we draw the possible forces, okay? So in this case, mg always there, and it is always vertically down, right? Mg. And then since it is on the surface that is inclined, so there's going to be this normal force perpendicular to the incline. See here, it makes 90 degree to the incline. That's what the meaning of normal force is, right? And okay, so this is long range force. This is a contact force. What are other contact forces here possible? Friction force. So it doesn't say anything about friction force. So if friction force is not there, then if friction force is negligible, then we don't have to worry about it. And this free body diagram going to be same whether object is going up or coming down or at highest point. Okay. But if there is friction force, then we need to know what direction it is moving. So for example, if it is moving up along the plane, then friction force is going to be down along the plane. Similarly, if it was sliding down, for example, if it was sliding down, then friction would be in this direction. So normal force, friction force, and what other contact force we need to think about? Is there tension here? No string attached, no tension force. And how about applied force? Is someone still pushing or pulling this thingy? We don't see anything in contact with this, so no. So these are the forces when object is going up, for example. So now how do I find net force is down? Okay. So for that, what I have to do is I have to find the component. See, this one is vertical, this is horizontal, but this is neither horizontal nor, should I say vertical for normal force? No, I should say perpendicular to the plane, parallel to the plane, but this one is neither. The mg or the weight is neither. It's just vertical, okay? So for that, what we want to do is, in inclined plane, we want to choose one axis in the along the plane. So here, let's say positive x is downhill. Yeah, you can choose uphill as a positive axis as well. And once you fix x, y is always perpendicular. So let's say this is positive y. So now you see normal force is along the y direction, good. Friction force is along the x direction, good, but weight, mg, is neither. So we need to find component of that one, okay? So to find the component, we need an angle. So here we know this angle here is theta. So this angle is always equal to the angle made by this weight force to this y-axis here. This you want to remember. So we can prove that using a little bit geometry, but I'm not going to do that here in the class. But if you are interested about the proof, I can show you proof. See me, okay? But for now, just remember it is the angle made by weight with the y-axis. So now it is something like this. So think about how we talked about finding components of a force. So situation is something like this. mg is the force. This angle is known. And this is, let's say, positive y-axis. This is positive x-axis. So to find component, we need to draw a vector, something like this and something like that, starting from tail to the tip. So we're going to be using a lot of component things. So you have to be proficient on component, okay? So remember, there were 6 different situations in one slide where I talked about finding component of a vector. If you did not do that, do the reading, watch the video, and completely learn it and become proficient, okay? So this side is adjacent to the angle, so that's why it's gonna be cosine component of mg, and this is gonna be sine component of mg. But in free body diagram, what do? We draw all the arrows starting from the object of interest. So object of interest is here, so we move this one over there and draw it there. So if I were to draw that, it's gonna be mg cosine theta here, and the mg sine theta here. Okay, it looks like f and mg sine theta, they're going to overlap. So let me make room for mg sine theta here. And this is f. So that's how you make the free body diagram of an object in inclined plane. And then now you can write equations. So for example, let's write sum of forces along the x direction is mass times acceleration in that direction. So in this case, let's find out the acceleration. Okay, let's find out acceleration. So how many forces are acting along the plane, which is x-axis we assumed? How many forces are there along the x-axis of our choice? There are 2 forces, okay? So for convenience, let's say friction is negligible, okay? For now, yes, we can include that later. So if friction is negligible, it's going to be mg sine theta, just one force, positive, is equal to mass times acceleration. We want acceleration, so that's why I'm leaving it as it is. So m cancels. So acceleration is positive g sine theta. You see that positive means downhill based on our choice. So acceleration is in that direction. So the acceleration becomes component of the acceleration due to gravity, a component of acceleration due to gravity. So that's how it works out, folks, for the inclined plane. So now, what if we include friction? So if you like to include friction, you can do that. So in that case, now mg sine theta positive. And if it is going up, friction is also down. So since we chose downhill as a positive, that's going to be that is equal to mass times acceleration. So now acceleration also depends on friction when there is friction. But when there is no friction, acceleration is simply g times sine theta. Okay, so that's on the inclined plane. So worksheet 3 already posted and supposed to be due yesterday, but since we did not cover all the material, I have extended that due date until I think day after tomorrow, or yeah, I think, yeah. So check the due date. So now you should be able to do that. So second question was about graph, which we already covered last class, and drawing free body diagram and writing equation is just like this. Okay, it's just like this, and that's what it is asking. So that's going to be good practice for you. And I'll also be posting feedback. So before you turn in, make sure to look feedback and make corrections if needed. But make sure you do it without looking at the feedback. Just copying the answer not gonna help you to learn. Okay. So here is another situation. Over there, it was inclined plane. Now there is inclined string. Okay. It is on inclined string. Usually object settles on vertical string like this. But if we apply force, for example, like that, then it can stay inclined. And that's the kind of situation it's talking about. Okay. So there is this mass and a force is acting something like this. So mass is given, which is 2 kilogram. Okay. And there is this angle. Let's say that angle is theta. So theta is 30 degree. And it's asking us to find force and tension. 2 things we need to know. So for that, we need 2 equations. Okay. So since it's a force is given and we are asked to find another force, remember they are related through the Newton's laws. So we need to prepare for using Newton's law for this. Okay. So for that, to use Newton's law, we need to draw free body diagram. So we replace object by dot. Oh, it was already dot, but anyway, so this force F is shown already there. And we know weight is always vertically down. Remember, this is not just mass, it is mass times G. Often is then forget about G, they just write M. M is not force. Mass is not force. When you multiply mass by acceleration, which is acceleration due to gravity in this case, that's when it becomes force or weight. Okay. and tension is along the string. So it is being held by the string, so the string must be pulling it up. Okay, so that's tension. So now, see, the F force, applied force, is horizontal, weight is vertical. So if we choose horizontal and vertical axis, then these two forces are going to line up along the axis. So let's choose that then. So let's say this is positive x, as usual, this is positive y. So now it tells me t is neither along our choice of x-axis and y-axis. That means what? When it is neither along the x or y-axis of our choice, we need to write its component. We need to find its component. So to find component of this, we need either this angle or that angle. So there is this angle. So which angle we know here? So this is angle made by string or tension with the horizontal. See, this is horizontal line and this is tension line. So where is tension line and horizontal line here in this diagram? There is horizontal line, here is tension line, so that angle must be this, not that one. So now this side going to be adjacent, so I can write t cosine theta, and this is going to be opposite, but we don't draw it there, rather we draw it here. So this is going to be t sine theta. Once we have this written in terms of component, we don't have to worry about t anymore. Okay, once we have components, we don't have to worry about force itself. So now when we look, what do we see? There are two forces along the horizontal direction and two forces along the vertical direction. So that means now we can write this equation. Since acceleration is 0, see, this is being held in a place, so this ball is not accelerating. So sum of forces along the x direction must be 0. Mass times acceleration. When acceleration is 0, the right-hand side is 0. So let's write this equation. Sum of forces along the x direction. How many forces are there in x direction? Can you count? Looks like there are two forces. One is positive F. One is F, that's pointing towards the positive x direction. And t cosine theta, that is pointing opposite, 0. So F is t cosine theta. So we know theta, but we don't know t. So we need another equation. So how do we get that? We repeat that along the y direction. So sum of forces along the y direction is 0, means, again, how many forces are there in y direction? 2 of them. T sine theta is pointing up. So since we chose up as a positive, I can say positive t sine theta. And then mg is pointing down. So up positive means down negative. So negative mg. And right hand side is 0 because acceleration is 0. Oh, it looks like from this I can solve for t. So we know mass, g of course, is 9.8 meter over second squared as long as we are near the Earth's surface. Theta is known, means you can find t and you can use that t over here, or you can combine this equation. So F is now t, means mg over sine theta, and then there is cosine theta. Okay, so you can just plug once everything and find F. So folks, that's how we use Newton's law when object is accelerating versus not accelerating, in when it is moving in horizontal direction or vertical direction or at inclined plane. So we covered all the bases, folks. So there is one more slide here, which probably I'll pick it up from next class. So here, what's happening is there are two masses moving in vertical direction. So for this, we need two free body diagrams, and we need to write equation, okay? So This problem is done in the note. You want to take a look. I may briefly go through this one in next class and move to the friction. Okay. So folks, I have Zoom hour today at 10 o'clock. You have question? Show up. If not, I'll see you next class. Have a nice weekend.